our next speaker is Sriganesh Kini. He works in the IP and broadband technology team at Ericsson. He focused on technology, strategy, network architecture, and the standards. Prior to this role, he worked on product development for multi-service edge and managed teams in IP routing in MPLS. So prior to Ericsson, he came to Ericsson actually through the Redback acquisition. And before that time, he also worked at Mahi Networks. Many of you may remember. And also, in the past, he worked in Bell Labs. Kini is very active contributor in IETF. Kini.
Thank you. I'll let you extend it. No, he's going to do it. Great. Hello. Good afternoon, everyone, and good morning to the people who are still in the US West Coast. I believe I have the best slot because I might find the maximum number of people who are awake. So the title of my talk is Cloud, NFV, and SDN. So it might be a bit strange that I don't have MPLS in the list of all the other nice keywords over there. So actually, I first considered having a different title. I thought it should be Delivering Cloud Applications using MPLS. But an application does not exist in a vacuum such that it can be moved to the cloud without any change. The analogy I would use is, let's say you're thirsty and you want to drink a glass of water. Now, if that water is on premise, somewhere at the back of the room, then it's a very simple, straightforward task. But if you have to get the water from the real cloud, then it's a lot more involved. It has to rain at specific times, at specific periods. Then there has to be storage and catchment areas. And then there has to be purification and delivery to the end user before it can be consumed. Similarly, if an application has to be delivered from the cloud over a network, then it needs certain functions, including network functions, which might be actually virtualized. So then I thought the title should actually be Using MPLS to apply virtualized network functions for application delivery from the cloud. But this entire process needs orchestration and control in a sort of SDN-like paradigm. But that architecture has always been in MPLS as part of the path computation element architecture. So I just removed the common MPLS from all these things, and I ended up with the title Cloud, NFV, and SDN. So in this talk, I will analyze some of the newer developments in MPLS that help to improve the application delivery over networks and see if we can answer the question, is MPLS the key to better application delivery from the cloud in the network of the future? So first, let's set the context in which we are going to talk about MPLS technology. Let me briefly describe the key components of any solution for application delivery. Central to the solution is, of course, the network, which is the glue that transforms an application from one that just runs in the cloud to one that provides the best immersive experience for the end user. To do this, the network should, of course, be programmable. But more importantly, it should be rapidly adaptable to provide the best user experience at that time. The network should have high availability, high reliability, provide end-to-end performance, and also SLA guarantees for that particular application. The next major component of this solution is the cloud infrastructure, which is a general-purpose application environment with open standards and technology and the ability to host virtualized applications, including the network functions themselves, to form the application delivery pipeline. The last component of a solution is the application itself, which evolves in functionality rather rapidly so that the newer application interface mashups can address newer use cases for the end user. Let's take a specific example. As we may all agree at this conference, the trend towards application delivery from the cloud is a dominant trend. It's going to happen. So I like to think of the application as decomposed into a pipeline of functions that range from the highly compute-intensive backend in the cloud, then other functions that are more network-like, or what are called as network functions, and finally, the presentation layer, which is typically your mobile or your endpoint, end host. This pipeline has to be created in a specific sequence in order for the application to be delivered with high quality to the user. Such an application pipeline is typically referred to as service chaining. So in today's talk, we'll examine a couple of MPLS transport mechanisms that enable this service chaining. And the two specific mechanisms are segment routing and VPN chaining. So let me first quickly summarize these two technologies. Firstly, segment routing, as it is very popularly known in the industry, or as it is known as SPRING in the IETF standardization body. SPRING, incidentally, stands for Source Packet Routing in Networking. Quite a mouthful. So it's basically a source routing technique, which is a technique that has existed from a very long time. But this time, it is applied to achieve explicit path routing. When it is realized using MPLS, it becomes a source-specified hierarchy of LSPs, where each LSP in the hierarchy traverses one segment, and then your end-to-end LSP is constructed. The key thing in this technology is that it improves the ability to innovate at the edge while making the core of the network even more simpler. But a more interesting aspect is that a label in the label stack can now be used to execute a certain function, a service function, a virtualized service function, whatever you want to call it, along the end-to-end LSP as the packet goes from source to destination. So let's take a look at this example on the left, where the packet is going from that LSR through the red LSR to the blue LSR. As the packet goes to the red LSR, there is one label, which is the purple label, that actually says that another additional network function has to be executed on the packet before it is forwarded to the blue LSR. Let's see the other technique on the right, that is the VPN chaining technique. In VPN chaining, there is a large amount of reuse of well-known BGP, MPLS, L3 VPN architecture to route the flow along an explicit service chain. The flow is first associated with a specific VRF at the ingress, and then the next hop in the VPN is chosen according to the service chain topology. At an intermediate node, which is the red PE LSR, the flow is associated with a specific VRF, and the next hop in that VPN is chosen to be that specific service, after which the packet is sent along to the next PE, which is the blue PE LSR. This is done in conjunction with certain policies that I'm going to talk about later. Let's dive a bit more into segment routing and see how it improves cloud application delivery. So one of the interesting results of using source routing is that there is absolutely no path setup required other than a one-time global index distribution in the network in order to create the labels. This is equivalent to having every path, and I mean literally every path in the network available at all times, in contrast to your typical traditional path setup, which is done on demand and requires certain actions to be performed in the network before that path is available. This is an extremely powerful concept in Spring. Let me just illustrate it with an example. For example, in the traditional way, if you wanted to do TE multipaths, then there is some significant improvement that you have to do in the basic protocols. This improvement has to be then implemented in all the different software nodes, possibly different implementations. There has to be interoperability, and all this has to be ensured before that particular technology is deployed in the network. But let's see what happens in Spring. In Spring, all these paths are readily available at all times. So there is no real state that you want to create in the network, as a result of which these traffic incident multipaths are directly available in Spring. Similarly, if we take another basic mechanism such as make before break, right? This is a very basic functionality that's needed to run your traditional network. In Spring, there is no path state that has to be created in the intermediate LSR for the new LSP. So make before break is really not required. It's already present by virtue of the fact that all paths are already available. But note, just because paths are available, it does not imply reliability, because network resources are required to meet the SLAs for those particular paths before that path can actually be used. This allocation of resources and ensuring that one allocation does not step over another allocation can be done through a centralized mechanism by just controlling the edges where the flows are mapped onto the certain LSPs. Also, source routing, by virtue of it being such a powerful mechanism, it actually has the potential of creating a loop through an erroneous or malicious label stack at the ingress. So just as they say, with great power comes great responsibility, there have to be mechanisms that ensure the integrity of the label stack as it is created. One could actually argue that this issue is inherent in MPLS. But note that deep label stacks have so far only been a theoretical possibility, but not really seen in practice in MPLS. With segment routing, since the label stack has a depth of the order of the number of segments, one has to consider ways to keep the number of segments and consequently the label stack depth to be bound in some way. Spring also has a simpler protocol stack because IGP is now used in order to advertise labels. But an operator needs to look at the operational procedures that are required in their network to verify that all of those operational procedures are being met through the new protocol stack. Let's see the other technique that we talked about for service chaining using MPLS transport, that is VPN chaining. So VPN chaining has the very useful property that it heavily reuses the currently deployed architecture and the operational experience. The underlying tunnel infrastructure can continue to be your traditional protocol driven, such as LDP or RSVP-TE. It can also reuse the VPN label exchange protocol, which is BGP. However, the choice of the VPN next hop is now determined by the service topology route targets. Policy is used to steer the traffic from one VPN through the service node to the next VPN to form your chain. These policies can be applied in a centralized fashion, like your SDN paradigm or your SDN architecture. But note that there have to be mechanisms in place to ensure that this policy-based traffic steering does not by itself end up creating loops in the network. There are some additional considerations beyond what we have talked about, which is applicable to actually both technologies. As we have seen in both segment routing as well as VPN chaining, there is a combination of traditional routing protocols, maybe modified in some ways, but still traditional routing protocols, and an SDN-like architecture. But you can call these SDN components by whatever name. You can call them as additional controller software, you can call them management systems, orchestrators, interface to routing systems, operational support systems. At the end of the day, it does not matter what that component is called. The key to keep in mind is that these additional components will play a part in determining the operational efficiency of your network. And additional tools may be required to troubleshoot your network. Today, when we talk about networks, almost every part, every infrastructure component is compared with its virtual incarnation. Virtual networks have been around for a long time. Then came virtual machines, then virtualized applications, virtual this, virtual that. There is no limit to virtualizing anything. But when something goes wrong in these systems, the pain to troubleshoot them is real. There's nothing virtual about it. Luckily, MPLS has a very long history of developing a very rich set of tools, and the standardization bodies have even addressed the requirements from other domains, such as the transport domain. There are still a couple of aspects that need enhancements. One of them is the in-band OAM channel for the LSP, especially when services have to be applied along the LSP before the packet reaches the end of the LSP. Another is load balancing when deep label stacks are prevalent. So let's dive a little bit in detail to understand what the issue is in getting an in-band OAM channel for segment routing. And let's also discuss some approaches to a solution. Now, the fundamental requirement for OAM is that the OAM packet has to follow the exact same path as your data packet, right? I mean, you need to do certain kinds of tests on your particular data path to see whether it is performing well. Is it executing? Does it have the delay that you expect? Does it have the jitter that you expect, and so on? But in the presence of services, those services should not be applied to the OAM packet, right? Otherwise, you will start getting NAT and firewall applied to the OAM packet, which is not a good thing. However, the OAM procedure should be able to give you information about the service itself, at least the basic information, such as whether the service along the LSP is alive or is not. And you should be able to still execute your end-to-end OAM procedures as they have been available. So one way to do this, and MPLS, that's the beauty of MPLS, that there are already existing mechanisms that can be used to implement these procedures. One way to do this is to define special purpose labels whose semantics are such that the label action procedures associated with the next label in the stack are not executed. This is a new thing in the MPLS architecture, but it follows the principle of what special purpose labels were originally designed for. The intermediate LSRs, that is the transit LSRs, they do not hash on these special purpose labels, as a result of which the OAM packet takes the exact same path as your data packet. However, when the packet comes to the LSR, or rather the service node, then it recognizes that it must not execute the service on this packet because it's an OAM packet, and hence skips that service processing and forwards that packet along the LSP. Now, at the end of the LSP, you might still have to recognize that it's actually a OAM packet and perform the actual OAM procedures. I have not illustrated that in this particular label stack, but that can actually reuse the existing mechanisms available in MPLS, such as a GAL or any kind of alert that you want to do. That is not key to the whole idea, but the key to the whole idea is that you should be able to not execute services on the OAM packet as it is going from one end of the LSP to the other. There's also another way to do it, which is a little bit, maybe a little bit controversial. So the alternate way to do it without special purpose labels is to actually use the TC bits in the service label. I have not shown that particular approach in this particular slide, but think of it as a certain annotation that is done within the service label for the OEM packet to convey the same information that you should not apply a service on this particular packet as it is going to the LSR, where a service is applied to the user packet. Now, it might be debatable whether the TC bits that are not at the top of the stack can themselves be used for hashing by the transit LSR. So that's something that needs to be discussed and further investigated. But that's another way to do it, even if special purpose labels are not to be used for this. The other key thing to consider is load balancing. Now, note that earlier I had mentioned that segment routing actually increases the label stack depth. And that increase in depth is of the order of number of segments that you have in the end-to-end LSP, which really depends on your network architecture and how many hops are there, how many services you want to apply to the packet, and so on. So it would definitely become deeper than what it is today. And that could be an issue with some of the hardware, especially older hardware, when it wants to do load balancing using entropy labels. Now, entropy labels is one of the key fundamental ways to do load balancing in MPLS. And the key idea is that you put a label to identify a flow, and the intermediate transit LSR uses that label to do a hash so that you spread your load equally when you have multiple paths. One might think that this problem actually disappeared in source routing simply because the source can specify everything, right? But that's not true. One of the key things in source routing is that even though you specify at the source the actual segments that it has to take, there can be shortest path routed segments as well. So the moment you have shortest path routed segments, you could have multiple paths within your shortest path routed segments, and you would have to do hashing and multi-path load balancing on that. Another key reason is that lags are very common. Link aggregation groups, they are very prevalent in networks today, and you have to spread your load on those lags using something like an entropy label. Since the intermediate LSRs or the transit LSRs need to access the entropy label, it should not be too deep in the stack, or they might not have the hardware capability to actually access the entropy label. So instead of putting the entropy label right at the bottom of the entire label stack, another way is to actually put it after every segment or below every segment's label in the LSP. But that again has the problem that your label stack blows up even further. So one of the ways to actually do it is to actually reuse your entropy label from one segment to the next, such that when the particular segment terminates, you pop that entropy label, but then reinsert it below the next segment's label. This way, the entropy label is always at a fixed depth in the label stack, and there is no issue with the transit LSR being able to access the entropy label, and there is no label stack explosion either. As one of the presentations earlier in the day, I think it was Bala's presentation, it said it takes 3 to tango. I believe that, though I suspect many might have a hard time even getting 2 to tango. So when you design your network to glue together the underlying infrastructure, the one key takeaway is that MPLS has the necessary infrastructure in it, but you do have some choices. So you need to make your choices carefully. Thank you.
Any questions? Okay, coffee break. Come back 3:30 exact. Thank you.